Hello, welcome to today's webinar. We'll get started in a few minutes. We'll let people hop in. While we wait, I'll introduce myself. I'm Jessica Finnegan. I am the Customer Success Manager here at Coreform. So if you're emailing or have questions, you're often interacting with me. So it's fun to see people come to the webinar. We'll just give a few more minutes while people pop in. Today's webinar will be covering an example optimization workflow using DAKOTA, Moose, and Coreform Cubit. So I hope you came to the right webinar. And a recording will be sent out after the webinar so that you can rewatch and have access to the entire webinar today. Okay. And so for today's webinar, we have, let's just take a look at the agenda. Today's webinar will be presented by Greg Vernon, as you can see here, and we will be covering problem definition, using DAKOTA, using Cubit and Python, using Moose, and then Greg will show us the results of kind of combining all these methods. And we, okay, so if you are new to Coreform Cubit, let's see, Cubit has features to import CAD models and clean them up for meshing. It has semi-automated hex meshing and allows control of mesh properties and excels with powerful scripting capabilities, especially with Python. So if that's interesting to you, feel free to reach out to us as well if you haven't used Cubit before. As an introduction to Coreform as a company, we are the exclusive commercial distributor of Cubit software. One of the best ways we have found to accelerate the adoption of Coreform Cubit in your company is through formal customized consulting. So if that's interesting to you, please also reach out. While Coreform is also developing world-class meshing software, we are also developing an IGA solver that removes the need to build a mesh without sacrificing accuracy or capabilities. If you're interested in IGA, please reach out to us directly and we can answer any questions you might have. So for the next part, we just have a short little introduction poll so that we can get a better sense of where you're kind of coming from in terms of your experience with DAKOTA, Moose, and Coreform Cubit. I'm just trying to launch this. 1 second. Okay.
And maybe as you're pulling it up, we've at least got one person in the Q&A who says that they can't hear us. Can someone maybe at least raise their hand in the chat or let us a message if you can hear us? Okay. Thank you.
Okay. And this will be sent out with the audio, so I apologize if you can't hear, but there will be a second chance. Okay. I'm just having slight issues launching the poll. Matt, can you see if you can? Oh, there we go. Okay, thank you. We'll just take a few seconds and answer those two really fast questions. It's fun to see everyone's answers come in. Okay, so it looks like most people have not used DAKOTA with Cubit or Coreform Cubit, so that's good to know. And we kind of have a mixture, but most people are new to DAKOTA as a whole. And then I will turn the time over to Greg so that he can get started with his webinar.
Thanks a lot. Jessica. Thanks everyone for your attendance today. So as we just mentioned, so the optimization problem that we're going to look at today is admittedly a bit of a contrived just example that we can kind of simply see how we would put this together in using these tools. This actually comes from an existing example in the Moose code. So this is it's a nano indentation problem. And what we want to do here is we have this nano indenter on the left with a few geometric features that we want that are design variables. And what we're going to do with this nano indenter is we're going to depress into the target material 2 units down and then retract the nano indenter. And we're shooting for a target that we'd like the permanent deformation to be at -1.5. And so our objective function here is going to be the distance, the absolute distance in this case. Of course, do that as like a square of the difference between the final displacement and the target displacement we had for the permanent deformation. And then we're going to be able to vary these 3 parameters. The RS is actually going to be a scale, so it's always larger than the tip radius. So we're going to vary that from 1.05 to 2. But it's kind of a large range of variation here, and then theta in degrees for this wedge angle here. And then just for the purposes of showing how you would impart constraints in this, we'll also put this reaction force constraint that we don't want to push too hard to be able to achieve this goal. So that's just a little bit of background behind this problem. And just to show one simulation of this, just from this, from our data set here, you can see that we depress in to 2 units, and then we retract out. And then there's this remaining deformation. So people who do nano indentation studies are probably familiar with these force displacement curves that we see here. I also want to mention that you'll be able to find today's example already on GitHub. We have a link down below for Coreform's public-facing GitHub's repository, and then this specific repository is called Cubit DAKOTA. I mean, we've just been putting this together just for this webinar, just for the last few days, and we intend to kind of work on improving this and maybe even updating with latest versions of DAKOTA that have been coming out. And so if you're interested to see how you could run these kind of studies, keep track of this repository. In particular, today's demonstration is using a workflow that I initially started using almost 10 years ago when I worked at a Department of Energy site as a contractor. And then I just kind of have been reusing this exact same workflow through my time at my former employer, and then in my graduate studies, and then now for this webinar. So as we update the workflow to maybe match new paradigms with DAKOTA, we'll make sure to capture those. So what I do is start off by introducing DAKOTA and some of the workflow considerations that we're going to have for setting up a DAKOTA study. So I know it's a wall of text here. Feel free to look at this in detail on a rewatch through. But the key things I want to mention are that DAKOTA is open source and developed by Sandia National Laboratories. It's now available on GitHub. While primarily execution, in my experience, has been always through a terminal, and creating input files for me is now just a matter of taking text files and using those as templates. They do have a GUI that can help support setting up of models, especially if you're new to DAKOTA, as well as they have pre-built binaries available for Mac, Windows, and various Linux distributions. And then DAKOTA has then all of these different kind of optimization capabilities, as well as uncertainty quantification, sensitivity studies, and on the optimization, global, local, surrogate-based methods. So it's really a powerful tool. It's been around, I think, now for almost 30 years. So if you want to get DAKOTA, their latest version 6.18 just came out a few years ago, or a few weeks ago, and I think is now officially been released. You can download either the source or these precompiled binaries from the DAKOTA repository on GitHub. You'll notice in the naming here, they've got your different distributions, as well as some of these will say GUI. If I zoom in here, some of these will say GUI or just CLI or GUI and CLI. So if you want to install this maybe on your Windows machine and have the GUI available to you, you might look for those under GUI stuff. But so I'm going to show a little bit of the GUI today, and that's where I got those GUI builds. I'll also mention that today, everything I'm running is actually going to be through, I'm actually running on Windows 11 using their Windows Subsystem Linux, or WSL, which gives me a Linux environment on my Windows machine. But the Windows GUI will be done purely in Windows. So one of the kind of powerful functionalities of DAKOTA that we're going to make use of today is what they call their black box interface, which allows you to essentially take any simulation tool that you might have, not have to worry about building it against DAKOTA or trying to link in shared libraries, but just using Python as a means of interfacing between DAKOTA and your tools. So here what we have is we're going to write a DAKOTA study, which is going to be an input file that is going to be parsed or processed by DAKOTA. DAKOTA will then be producing variables and then passing those variables into our Python via file transfers. So we'll be writing out, writing files to disk with your variables, reading those in through Python, and then hitting our simulation model, which in our case is going to be driven by Python. It's going to run Cubit Python, and then using sub-processes, we're going to launch Moose. Of course, if you have Slurm on a machine, there are Slurm modules for Python, and you could use, I think it's even called SlurmPy or SlurmP, and you can then run Moose from there. And then your results are going to be also saved, excuse me, will be saved to a text file that DAKOTA will read back in and make its next guess or its next iterations. So really all you need to do is be somewhat proficient at Python, or at least able to modify template files that someone else has produced. So kind of showing a bit of an overview behind how I've structured this code or this example using the black box interface is that we're going to have a .in file, which is going to be our indenture study, where we're going to define DAKOTA specific inputs. So this will be passed as an argument in the command line to DAKOTA. Then the black box interface has a few kind of just templated files that we only require kind of minimal modification of. In fact, these were produced by the DAKOTA GUI through a wizard. And then in future studies, right, I just have pulled those files and just change a name here or there, change a variable, so minor modifications. And then that black box interface does our evaluations. And this is where we provide kind of all of the files that are needed to actually run our simulation. So I have gotten into the habit of calling a Python script an evaluate iteration.py that's kind of like the master, and it imports and runs different routines as needed. This .i file is our Moose input. So then looking at just kind of the script overview of evaluate iteration, we're going to read in that parameter file that I mentioned is written out by DAKOTA. It'll fit the template of params of this params.template, which I'll show in a bit what that template looks like. But then I just got routines for, say, building my model, which is going to call Cubit, submitting Moose, which again, I'm going to use sub processes, but you could use like SlurmPy, computing objectives and constraints from the results of your simulation. writing those results back out to a file. And then it'll return back to the black box interface, which we'll call back to DAKOTA. So this is a fairly good kind of template that, you may not be using Moose. You might use a different solver. Maybe you're not going to use Cubit. Maybe you're going to use some other tool. This is a pretty general kind of workflow from what I've found. So we're going to talk about using the DAKOTA GUI. So if you launch the DAKOTA GUI, you should see a window that looks something like this. The first time you open, you'll have an empty project explorer. And as I mentioned, there's wizards, and I'll actually now show this. So if we were to create a new DAKOTA project, we'll have a wizard that pops up that asks us to provide like our project name. So maybe we'll call this nano indentation optimization. And then we can do things like create maybe a new DAKOTA study and walk through this wizard here. So rather than bore everyone by going through each individual step along the way, what I'll just mention is that some of these examples of just how helpful these wizards are is they walk you through even like, what kind of solver should I use? And so the fact that you're able to tell it, I want to do optimization or uncertainty quantification. Maybe I know that I've got a local optimization problem, or maybe it's a global problem. Just walking through these things, and it suggests to you which method to use, and then it walks you through creating your variables, specifying what kind of variable it is, maybe defining your initial bounds. The check marks here, you can either enable or unenable or disable different variables along the way. The wizards are really fantastic in the DAKOTA GUI. So for anyone who's worried about, that DAKOTA might seem intimidating, the DAKOTA GUI does a really good job of simplifying it for folks. So what that then does is, as you get through those wizards, it'll update your project explorer. And so this is actually the result after I created that DAKOTA study here, that it's created my input file, this indenterstudy.in. It's filled out these different sub-objects: environment, interface, method, model, responses, variable. But you'll notice the text input file that corresponds to this, you can also preview that, but you can see these different sections here. So like environment, method to method, model to model. And so it's kind of like a one-to-one mapping here. So I just even find this like really helpful for, if you're like me, you kind of like working in text files a lot, and it is still kind of nice to have this little project explorer that helps you kind of at least see what options are available. So anyways, I found this was immensely helpful when I was first kind of starting using DAKOTA, and I think a lot of you may find that helpful as well. It really simplifies a lot of the initial setup. And then once you have the main most of the setup, you can then go to their fantastic documentation and learn more details about specifics behind the different objects. And they even have built-in help into the GUI. So I think most of these spots, there's like a question mark that you can like click, and it'll bring up a help for you. So it really is fantastic. I cannot recommend the DAKOTA GUI enough.
We had one quick question, Greg.
Yes.
He said, I'm new to DAKOTA and Moose, but what is the difference between DAKOTA and Moose?
Yeah, so that's a really good, that is a really good question. So what I would say is DAKOTA is a kind of a method at the heart of every optimization problem. You are evaluating objective functions. And those objective functions might be running a simulation to get off some values and determine some stress values as maybe a constraint. Maybe I don't want to yield. But if you have like one variable, you might have to write in Python, you might write your little bisection method to try to optimize to a solution. DAKOTA handles all of that optimization like methodology. So you get access to a whole bunch of powerful optimization tools like surrogate models, local Newton solves, genetic algorithms. It handles all of that for you, as well as it handles job submission. So they have tools that can help monitor whether or not a job failed or not, and whether or not it should resubmit. There are ways to have DAKOTA even, I think, work with your Slurm directly. So DAKOTA is like this overarching kind of workflow manager. If you're familiar, some of you may be familiar with iSight, which I believe is distributed by Dassault Systems. DAKOTA is essentially the equivalent of iSight, where then Moose is the solver, where Abacus might be the solver for an iSight type of problem. Now, I will say that Moose does have some internal capabilities for doing optimization, which, if they have built-in optimization things built into Moose, you may just want to choose there. I've chosen to use Moose because it's open source and it helps us demonstrate just the power of using DAKOTA. If you say you use a different open source solver that maybe doesn't have the optimization capabilities, like say Elmer or Phoenix or Firedrake, that you could use the exact same DAKOTA kind of workflow for all of these different tools. So hopefully that helps answer your question. So what I want to talk about next is just where we've used Cubit kind of in the loop. So we're going to get to the Moose, but in order to get to Moose, we have to have a mesh file created. And so just as a comment here that I'm not going to go too deep into all the different nitty gritties of using the Cubit Python API. We have several webinars that are available on YouTube. If you just go to our to our YouTube channel and search Python, you can find many of those that talk about the different things with the Cubit Python API, as well as we have a dedicated section in our official documentation for the Cubit Python API commands. So I will reference, or I'll suggest that if you want to learn more about the different Coreform Cubit Python API functionality, that you look at one of those sources. So with this problem, one of the things I ran into is I wanted to mesh the model. And I was basing this again off of the mesh that was created by this is an example that actually lives in the Moose example problem sets. And actually this mesh in the middle is the mesh that's included with their example. And if I look at this, I've got maybe some quad elements that are almost inverted already. So it's maybe kind of low quality. Again, they're trying to get rid of elements in places we don't need them. We want to have a nice mesh density near the tip of both the indenter and of the target material. If I use the same initial mesh size that they have before they try to go coarse, I get a really, really fine mesh. I've got way more elements than I need. And in regions that don't really change, I don't really need that for. And then if I just use maybe biased meshes on curves, maybe still don't quite have enough local control, that maybe the mesh is growing too quickly, maybe for my liking. And so this is one of the things that's kind of unique with Cubit and the ecosystem around Cubit, is the ability to use what are called sizing functions, and specifically from the Exodus mesh files. So Cubit was built around Exodus. It is the native mesh format for Cubit. And Cubit supports bringing in a mesh file that has at least nodal variable values. It might even be able to take in element variable values, but it can read those as a field that we then say, I want this field to be used as a mesh density field. And you can scale it from a minimum value to a maximum element value. Exodus comes from the CKIS project from Sandia. And again, for those of you who are familiar with Cubit, you probably are aware that Sandia National Labs develops the government version of Cubit, whereas we're the exclusive commercial distributors. But so that CKIS project contains commands for being able to build Exodus, which comes with then a Python module. And so once you have that Python module, you can import it and do things like, say, import an existing mesh that maybe you've just written out from Cubit. It has no variable data on it. You can write your own function. Here I'm just using a random number generator to compute some NumPy array. And then just a little bit of boilerplate to then add that array back into the XS file and close it. Once you've saved out, so this close now has saved this XS file, we can then read that mesh back into Cubit through this import sizing function. And we tell it that I want to read in maybe the variable mesh size as what I want to use as like the scalar field here. And then I'm going to say use the minimum value. So normalize this, the minimum value of mesh size corresponds to this min size, and then max value to that max size. This is also documented in our manual under the mesh operations, adaptivity, and sizing functions, and then this XS base field function here. And there's a link as well. So you can learn more about this there. You can also use this just if you run a simulation and you have out maybe say plasticity or von Mises stress or like element error fields, you can just even remesh based on your solution results. But this XS Python module allows us to just be able to use now suddenly Python to define an arbitrary field. Oops, and I think I lost I had a picture of this, I thought. Oh yeah, I guess this was the picture. So this is what I did here is actually, I was able to write some Python code, some logic that if I'm in the region of the tips, I wanted to keep everything to the same mesh density, this nice fine mesh density here. And then as I grow away from this boundary, I want to then, increase my mesh size. That's a problem with doing zoom in PowerPoint. But so you can see here, I've now got a nice kind of gradual distribution or increase of my mesh size, which means I get a relatively higher mesh quality than I might otherwise get. And since we've already committed to using Python to run the DAKOTA as well as execute Moose and run the Cubit Python, it's just kind of natural to be able to use this XS Python module as well. So we'll probably do some more webinars and discussions on the actual XS sizing functions. We found some customers that found them really useful. So then as I come back to where we're going to use Cubit within our DAKOTA routine, I've got a couple of these Python files I said here that are inside the evaluation, that where we said I want to say build my model, I call off to the spherical nano indenter, which builds my indenter. Part of the contents of building this indenter is to go off and run this mesh sizing function, which imports a temporary XS file, computes the mesh, puts that mesh size back into the variables, and then I read that back in at the very end. And again, you can see this pattern in the full code. I'll give a preview of the full code in a little bit. But that's just like the general kind of workflow where it's still all inside of Python. I can run Cubit inside of Python and the XS inside of Python. And you could probably use DAKOTA someone actually asked if we could use DAKOTA to optimize the meshing setup in Cubit. You probably could use DAKOTA in that manner. And I haven't personally tried that, but I believe that is possible. I think DAKOTA even has a built-in block for actually executing Cubit. I have not personally tested that though. Okay, so next I'd like to just talk a little bit about Moose at a high level. So again, Moose is another open source finite element code. It's developed by Idaho National Laboratories. It's available on GitHub, and they support Linux, Mac, and Unix, as well as they officially support Windows WSL, or at least they provide a very robust process for installing Moose on your Windows WSL environment. They have a really active forum, which I've found helpful to answer questions about how to use Moose and how to run Moose. And Moose has this native support for the XS file, which again is that native Cubit mesh format as well. So if you're using Moose and Cubit together, it's kind of a natural harmony. And so if you want to get Moose, you can just search for Moose, Idaho National Labs, or here's like the full web page for it. And they have like a good getting started section here. And then just as a note, one of their contact module has this example that I pulled this optimization problem from. So if you want to see what that looks like inside of the Moose distribution, you can find it there. So I've made some modifications of this problem for ours, but just as a heads up for where that's come from. So what I want to do now is I'm going to maybe leave PowerPoint for a little bit, just show a couple of these websites I've been talking about, just to give a bit of a feel for what where you can find these different things, as well as then show you the code that we built in Python for this. So to start, so we start with the DAKOTA. So again, if you go to DAKOTA's main webpage, they've got kind of their news and their announcement of DAKOTA 618 being released. But if you go to their downloads, they then will direct you to their GitHub releases page. And so now DAKOTA is being distributed through GitHub, as well as their, you can see like the source code that's being worked on, so you can contribute. They also are using the discussions page for as like their forum. So it's pretty vibrant. Let's just go back to those releases here. So if we wanted to say download, this is where you could get the GUI for Red Hat Enterprise License 8, or you can get it if you show all 16 assets. Here's where you can get like the Windows installers. On the CCUS front, again, if you search Sandia and CCUS, you'll be presented with this web page, and there's a link in here for Exodus that then walks you through how to just build the Exodus Python kind of utilities that you just need. And so once you've done that, you can then find the Exodus Python module. Also, through their web page or through their GitHub page, they have their documentation, and there's a link in here for their Exodus Python interface, which then gives you access to their API if you're interested to know, say, how to open an Exodus file and with different kinds of modes. So to open it with, say, a NumPy array mode, as well as to how to, say, get times, put new times into maybe a result file, get the coordinates of your mesh nodes, get node variable names and numbers. So there's a lot of functionality in here. So you can actually now, and what we'll use this also in our DAKOTA for, is that when we run our simulations, we have Exodus files as output. We're actually just going to use this Exodus module to, say, grab the nodal variables at, it's like the nodal displacement at the node that we care about. So you can use this also for post-processing. So if there's any graduate students in here as well, this also makes Exodus a pretty enticing option for writing your graduate final element codes with. And I give a little bit of a walkthrough as well on our. This will work. I have a little bit of a README here. Again, we'll flesh this out a little bit further, but a few instructions for how to find all of these tools and where to find different installation stuff. So again, this is going to be a bit of a work in progress. Hopefully should get better as time goes on and as we get contributions from other folks. But just wanted you to be able to see how we built this this example. So then just a couple of things I wanted to just walk through. I mentioned in the PowerPoint, so I'll pull it up here. I mentioned a few things regarding there's kind of these black box interface tools. So again, using the GUI, it created for me like a params template. And that is, all this looks like is whatever the variable is that you're referencing in your indenter study or your input file, you just essentially put within curly brackets. And this is the template that the code will look for tip radius, and it will put in the current value of tip radius into this slot. There's a quantity of interest extraction routine that you don't have to modify at all. You can just take this verbatim as is. And it just handles when you are writing out results to a text file, it's able to parse that text file. And then it also produces a DAKOTA interface.py file or .python file. There's a couple things that you'll notice around if you look at these if you work with these scripts, that for now, I've hard coded in paths. So for instance, there's a DAKOTA Python location, and I've hard coded my path to where that DAKOTA Python lives. So in the current instantiation, you would need to update this with your own paths. But you can see here that then this is where we use that QOI file that we say, I want you to look in the result file for reaction force. And then this kind of gives some instructions for how it then extracts out. So in this case, we're going to have one line that's going to say reaction force, and then a space, and then a float. And it's going to be able to read that in and assign that to be the reaction force. And then the same thing here with that depth error, that gap that I was talking about that we had. But otherwise, everything below kind of this section here, you just take verbatim. I mentioned we have our input file. Again, we produce this primarily in the DAKOTA GUI, and then with some updates. But you do want to do things like, say, link files that, I don't want to have to maybe copy my input file over and over and over. So I can maybe just link to the top level input file. If I was making updates to that input file, so maybe if I was using Apri Pro, for those of you who are familiar with the Apri Pro tool, then I might need to copy this file to each local running directory. So Moose will handle creating a temporary directory for each of your evaluations here. So you don't have to worry about, after running, you have to worry about like cleaning stuff up if you don't want. So again, just more of the stuff that DAKOTA handles for you, and you don't have to worry about writing your own logic for. In my case, I was running this on my desktop. So while I could have run these evaluations in parallel next to each other, I chose to run each evaluation serially, or I guess in sync. So one after the other, but then I ran Moose in parallel with MPI. But when I was doing my graduate studies and I was running on a large cluster, I was able to run 20 or 100 evaluations at a time. That really sped up everything for me during my thesis work. So there's a lot of good information in here. The last thing I just wanted to show is just this DAKOTA, inside the DAKOTA GUI interface here. By clicking on the user guide, you can find a lot of stuff about the actual DAKOTA input file and like keyword references for a lot of the different things. We can like say go into a method and we can look at maybe the efficient global. There we go, efficient global, which is the method that I used for this. And you can find a lot of information about the different keywords and what they're compatible with and how they work. So I highly recommend. I mean, their documentation is also fantastic. And then on the QOI, that's a priori. So you kind of know that I'm looking for, I have an objective function that is measuring displacement, or I have a constraint function that's measuring maximum von Mises stress, and that's the quantity of interest. You kind of know a priori, but the solver is plugging those back into the file at the end of its execution for DAKOTA to then read.
And we just have one question. What exactly is a QOI file?
Yeah, so QOI stands for quantity of interest. And DAKOTA just calls this a QOI.py. So it's just a Python module that uses regular expressions to just parse a structured formatted text file. So I think I've got an example I can just show here. If I go into my work directory for the simulation that we ran here, go into one of my runs. So in this case, this execution spits out this output file that says depth. So I got depth error, a space, and then a float. Reaction force, a space, and then a float. The QOI.py is referenced by the DAKOTA interface to read it, to know how to read in that interest file. So that's what that's doing. Is it saying look for reaction force, And the DAKOTA GUI helps you build this QOI file. It like walks you through, and you can like get a preview of what that looks like. But if you notice just side by side here, I've got reaction force, and then I'm looking for one field after, right? So I'm going to store it, I guess, in reaction force. I'm looking for the one field after the text reaction force, which is what's matched here. So then this is the one field that's after that. So again, you can have any number of quantities of interest. They could be objective values. They could be constraint functions. They could just be, I want to maybe like track the simulation time, or I want to know the number of nodes that I used. Maybe I want to know the how many elements I had in my model, because maybe I'm doing a mesh convergence study, and I want to eventually be able to plot number of elements versus error or versus displacement. So it's really anything you want to be able to do something with at a higher level inside of DAKOTA within that input file. DAKOTA even has, I think, a method for Richardson extrapolation to do and to automate convergence studies. So that's just what that QOI file is. For the most part, you should not have to worry about actually editing the QOI module at all. All of your stuff is going to be handled by modifying, in this case, like this indenter study. Maybe I'll just pull it up here so we can get better formatting here. So what I've defined here is, I've got my tip radius, my shaft radius ratio, my wedge angle, provided those initial bounds. And what's happening here is I've got these responses, right, that are called depth, error, reaction force. And so these are what are kind of tying across the different routines from what I'm going to be querying. So this reaction force here needs to match the fact I've got a descriptor of a response called reaction force. I think I've actually got these mixed around, but so I'll probably have to make a slight update. But anyways, that's the idea of how these work with each other. So hopefully that helps answer. Yeah, so, and Thomas asked the question about, using these quantity of interest files instead of a Python parser. So I at least do it because this is a workflow that I originally kind of built for myself in 2013, and it's just been kind of familiar. And my life since then has just been a matter of copying and pasting these. I did notice in 6.18, there's now new workflows that are suggested. And so this is not maybe updated with how the latest DAKOTA kind of recommendations might be. So that's where, as I mentioned, I'm looking forward to updating the actual our repository here with some of the latest stuff from the newer editions. Also happy to take any merge requests from anyone who maybe is a DAKOTA expert and can support that. But what I want to get the point I wanted to make in this, though, is that Python is a really helpful glue tool that allows us to stitch all these different kind of disparate tools together. And then DAKOTA is this really powerful tool that helps do everything from optimization to even there's a nice little utility if you're doing just like a design of experiments. I think there's even like a let's see, like a list, like a list of parameter study where you can just provide a list of values you want to evaluate, and that could be like in a text file. And so I've done like just parameter sweeps. You can automate the determination of those points with like these centered parameter studies. But if I specifically have maybe 35 specific models I want to run, I can just put them in as a text file or as a list of points and just let DAKOTA handle all of the kind of the directory creation, cleanup. So that's really what I wanted to show, is that there's a lot of functionality within DAKOTA that you could probably make everything I've shown even easier. But with Python, just about anything's possible. I've at least found that this workflow works for me as far as being able to just update a template from study to study. So hopefully that helps answer your question. So the last thing I want to do, and then I'll answer the rest of the questions in a dedicated Q&A portion here, is I just want to show at least now the final solution. So computes an optimum. It just so happens this optimum that it finds happens to be at one of like the extreme bounds. So sometimes that happens, especially in a kind of a contrived example. But the key, as I wanted to mention, is that by using, in this case, I used the efficient global method. So it uses a surrogate model. After doing 4 initial full evaluations of moose, on every subsequent evaluation, it's running a surrogate, or it's updating the surrogate model and evaluating it and performing a global optimization on the surrogate models, which means I was able to do a lot more studies or evaluate a lot more of this search space using those surrogate models. And it's really fast. And I didn't have to worry about myself learning how to implement this Gaussian process surrogate model. I could just use DAKOTA and DAKOTA's implementation to do it for me. And so in total, this entire optimization took about 6,000 seconds, where almost all but 11 seconds of that time was actually spent running the meshing and moose part of it. So the surrogate models ran like in 11 seconds total. So it's really a low overhead way to get improved convergence on these kinds of problems. So you can see here, I ran 1 concurrent evaluation, and then I ran moose on 4 cores on my little desktop here. So all in all, not too bad. In about 2 hours, I've got computed optimum. And then just to show off the final solution here, okay, we can see we compress it down to 2, and then we relax, and it stops right at 1.5. So we've hit our target here. We play it one more time for us. Okay. So with that, I guess I'll just maybe close with mentioning that you'll be able to find this webinar as well as our past webinars on YouTube by going to our channel. And again, if you want to learn more about the Python, I recommend that you search for the Python on our channel. You find a lot of stuff there. And you'll soon be able to find this webinar as well. So with that, I think I've got some time for questions. So hopefully that was a helpful introduction to folks. Feel free to reach out to us on our forum if you have, or YouTube comments if you have any other questions that you'd like us to help answer for you. So with that, I'll start answering questions. So one question is, what's the advantage of using DAKOTA versus maybe the SciPy optimize? And again, what I would say that an advantage of using DAKOTA is that, especially for when you have like a compute cluster and you want to be able to submit jobs, to like a Slurm queue, just DAKOTA's got a lot of utilities built into it that help with managing those sorts of jobs, as well as handling your working directories, so you don't have to worry about writing your own file cleanup, or making sure that I'm not going to overwrite a previous job. If I'm running asynchronously, if I'm running maybe 100 models at the same time, I don't have to worry myself about writing logic to give unique names to all my different files. DAKOTA handles all that kind of stuff for me. So I'd say those are kind of, I think, some of the biggest values behind DAKOTA, is just that it handles a lot of the kind of nitty-gritty things with sub-process management and job management, in addition to having then all of these great optimization methods and stuff. Advantages of Moose compared to other open source file element packages. So I'll give at least my thoughts on advantages. I think all of these open source codes have different benefits and advantages. Moose, I think, really shines in a lot of multi-physics applications that are relevant to nuclear energy applications. It's also similar to Phoenix, whereas Phoenix is, I believe, a Python-based code that allows you to write your PDEs. Moose has the same kind of functionality where in like one line of C++, you can add a kernel of a, say, like a weak form of an equation. And so it's really easy to extend if you need to add new physics. And then it's got a lot of scalability that's been built into it as it's been developed by Idaho National Labs. I found it converges really efficiently on multi-physics problems. And then, of course, it's based on Exodus. And then Exodus allows you to use a Python interface to interface with it. So I just personally find it really helpful or really useful. Okay, and we answered this one live. Let's see. Yeah, so then for the optimization module, question was whether or not you could use it for topology optimization. I don't believe it does support that yet. I could be wrong, but my understanding is that topology optimization is oftentimes done with like SIMP methods. I don't know that they have that yet. It might exist, and there might be. I might just not be aware of how you can tie different optimization techniques together to effectively do TO for you. But it's certainly not like a Tosca type of tool for doing a topology optimization type of study. One question was asked whether or not we ran this geometry with IGA. So I did not run this problem with IGA. Some people might be aware that we've actually at Coreform have added to the Moose, or we worked on some projects to add smooth spline basis functions to Moose, and so you can run isogeometric analysis in Moose. I did not do that here, partially because since people had taken the time to build that example file in Moose, I didn't want to change too many things with regards to like the basis. What I might have expected if I maybe was doing this with IGA is I would have felt comfortable using instead of linear quads, I might have used quadratic quads that were then smooth, and I might have expected better performance on the on contact. I did notice the hardest part with this problem was a lot of contact chatter, and so it took me a while to kind of dial in different contact parameters, and so maybe it wouldn't have been quite as difficult. Yeah, so then there's a question about where you can find more demos on what DAKOTA can do. And I would say find the DAKOTA website, their documentation they have tutorials and examples, not just using the black box interface, but also using like built-in, so let's go DAKOTA. Yeah, but also using like if you've like linked against DAKOTA with like with one of your applications. So they've got a lot of good examples in here. And so that's where I would direct you to, as well as then to their forum. Yeah, so Gregory's asked whether I could highlight portions of the code that you'd substitute if you use a different solver. What I would say is that there's really one spot that you would need to change. And I kind of show this a little bit here in where you're doing the function evaluation. So in the main function that gets evaluated, which is in this case evaluate iteration.py. So right here, I mean, if you're using a code that doesn't support Exodus, maybe you're not using Cubit, this build model, maybe you use PrepoMax, maybe you use FreeCAD to build your mesh. So you might update this with whatever your preprocessor is, and then you would update this instead of being submit Moose, it would be say submit Elmer or submit Phoenix or something. And so then it just shows up just to show in the full code here. You can see that I'm then running this just through a sub process here. So I'm not making use in this example of any of the advanced Slurm type stuff that's available. But this would be where you would make your edits. Would be these two routines, as well as then if you had a different mesh format, right? If you need to compute that objective function based on results, you would change some of these too. but this is primarily, I think, what you're asking. So yeah, so someone asked about whether or not the software is free for download. So both Moose and DAKOTA are open source, free to download, free to use. The Exodus Python module through CCAS is also open source and free to use. Coreform, while it's a commercial solver, some people, or commercial meshing tool, some folks under government contracts can have free access to the government distribution of Cubit, but we also provide a Learn edition of Coreform Cubit, which is limited to 50,000 elements on export, but it can at least help you get started. Like most of the meshes that I ran for this example actually were under 50,000 elements. Then get you at least started with building up your workflow, as well as you can reach out to us for a trial license. But Coreform Cubit is the link in this that is not free. So let's see, we've answered depositimization. And then let's see, let's clean up some of these questions here. Someone's asked to see the Moose input file, so I'll go ahead and show that. Again, you can find the full Moose input file, or the original Moose input file, on the from the Moose repository, and it's in our GitHub repository here. Oops, that's not it's this one. So I've renamed it to Indent Power Law, or Indenter Power Law. There's also a crystal plasticity model that I did not put together, but I've got in this repository. But so it kind of looks like this. Again, it's user readable or human readable with kind of like blocks for different sorts of parameters. So defining where we're going to read in our mesh, defining that's going to be a 2D axisymmetric problem, defining functions for applying our displacement boundary conditions, applying boundary conditions, defining contact, applying materials. So that's all in here. Exporting out an Exodus result, stuff like that. Yeah, so then one more question was around whether or not the specific submit Moose was running it for local machine. Yes, I was running that on my local machine, so that was specific to that. In my former lives, when I used to run on HPCs, I would use SlurmPy for submission, but I think even that's now been superseded by some built-in functionality in DAKOTA. So I don't even know that I don't know that I would need to do SlurmPy today. But yeah, then DAKOTA does handle kind of the checking to see whether or not the simulation succeeded or not. So if it fails, I tell it to just insert a very large objective value and just move on. And so DAKOTA handles that for me. Yeah, so someone else has asked if you could use something like a CAD macro in this workflow. And so I did do that actually in my CAD workflow here. So I'm actually building the geometry in Cubit. So I've done, based on certain parameters, I can actually go through and create my geometry, and then I can name, sets as I create them. And that kind of helps get away from some of the ID kind of issues you have. So I can rename the surfaces. So again, in my master's work, I used FreeCAD with DAKOTA. And so I just used a FreeCAD Python macro and instead of Cubit for building the geometry. So yep, that's possible as well. Someone's asked a question about using Idaho's Raven versus DAKOTA. I am not familiar with the Raven project from Idaho, so I can't comment there. Again, links for the downloads. If you search for GitHub, or if you search for Coreform on GitHub, you'll find our Cubit DAKOTA. And then in this project, in the README here, I've provided the links to get applications and stuff. And then a final question, right, as we hit the top of the hour. Someone wants to know how you can verify the script used by DAKOTA successfully executed. Yeah, so that's where Let's see. So in the input file, so I've put a thing in here that says, on failure, what do I want to have? Or what do I want to have happen? In this case, I want to try to recover by providing a value of 2.0 as the objective function. So kind of saying like, maybe like the mesh just doesn't generate. I could have had like a retry, and I like retry like, you know, with a different random number generator for the different mesh. In this case, I just said, if, you know, if it fails, just give it a high objective function value that that means we'll just kind of like throw this out and then move on. So DAKOTA handles that for me. And then lastly, they also do provide like as these simulations run, they spit out standard out, which I usually always pipe to just an output file or like to a temporary file here. So you can track your DAKOTA as it's running along and see when it, if you have any errors. Again, I don't think I have any errors here. So zero errors. If you had an error, it'd be in this error file. It also does write out a restart file as well. That's an option I set in my input file. It's a binary, but if the power went out, I could always restart halfway through or wherever I was at in my model. So anyways, hopefully that answers most of the questions that people have had today. The curly braces, again, are just F strings. So these are just variables that are being passed in. I'm using F strings in Python to then evaluate them. So anyways, with that, I'll close down questions because we could probably should close up the webinar. But if you have more questions, please do reach out to us on our forum or leave us comments on the YouTube video when it's posted. So with that, I'll turn it over maybe to Jessica for any final thoughts.
Thank you. And I will send out links and a recording this afternoon to everybody who's registered. So you'll be able to look for all of that in one email. And thank you again, Greg. This was fantastic. If anybody has any ideas of future webinars you'd like to see, please contact us. We are always very interested in your feedback and your ideas. Thank you.